Yeah, you are the host now.
Okay, shall we start?
Yeah, we can start. Yeah.
Okay, fine. Yeah, good evening, everyone. So last week we have seen the basics related to the short circuit analysis. So today in the today's session, we will try to cover up the how to perform the short circuit analysis. Okay, with an example on how to perform the short circuit analysis using IEC 6090 standard. So during this, we will again go through the modeling requirements to perform the short circuit analysis and the input data required for performing the short circuit analysis. Okay. And in this session, we will try to perform the device duty calculations, which will be useful in order to understand how the switchgear ratings or the circuit breaker manufacturers select the rating of these equipment. Okay, then we will run the short circuit calculation as per 60909 standard. And then further, we will run the short circuit calculations and we will try to find out various fault current values, such as uh, three phase line to ground, line to line, double line to ground, which these details are helpful to determine the settings of the various protection devices. So directly, let me switch on to the ETAP window and let me share my screen. Okay, hope my screen is visible.
Yes, sir.
Okay, right. So I will try to explain the same in the ETAP software itself. So wherever it is required, we will try to note down some key important points related to the short circuit analysis. Okay, so just before to understand the system, first let me draw a single line diagram so that we can perform the short circuit calculations. So let me create a single line diagram here. So here what I'm doing is I'm keeping a circuit breaker, which is of the high voltage circuit breaker, and I'm connecting to the bus, and the bus voltage I'm assuming it as a 33 kV. Okay. And here we have a transformer, assume a transformer, and again on the transformer LV side we have the circuit breaker, which is connected to, let's suppose this is of 6.6 kV bus. I'm assuming the transformer rating as 25 MVA. So the rating of the transformer is 25 MVA and the impedance is the typical impedance I'm assuming. So it will automatically take it from IEC 60076. Okay, table 5. Right. Then again on the 6.6 kV side, let me connect a motor and again a lump load, for example, and connect a transformer also, two winding transformer. Okay, fine. And on the transformer LV side, again, let us connect LV circuit breaker. This is the LV circuit breaker. Okay, and connect this to. So very simple network I am taking. And on the LV circuit breaker, again, connect this is of 415 volt, right? So 0.415 kV. And the transformer rating, I am assuming it as, let's suppose it's a 2.5 MVA transformer, which is of 6.6 by 0.433, which is the no load voltage is always greater than the rated voltage of the transformer. And here, let's assume a lump load of, for example, it's 1 MVA. 1 MVA, and the power factor is same, it's okay. Fine. So coming to this, the motor, let's assume I'm assuming it as a 250 kilowatt motor. 250 kilowatt motor here. And okay, let's connect the circuit breakers here. I forgot to connect the circuit breakers. So connect. So connect the circuit breaker to the motor and connect it to the bus. Similarly, introduce a circuit breaker in the lump load. Perfect, fine. So assuming the lump load as, let's suppose, some 10 or 14 MVA, whatever it may be, we can assume. So 14 MVA. Okay. Now what we will do is we will replicate the same network. We will replicate the same network on the other side also. So span this 33 kV bus and control C and move from dumpster. Okay, and connect it to this 33 kV. Right, fine. So from 6.6 kV, let me introduce a bus coupler, or we will call it as a tie breaker from bus 2 to bus 5. So take one bus circuit breaker, rotate, connect to this, connect to this. Similarly, on the 415-volt side also, let me connect a bus coupler. Fine. So coming to this is the grid. Okay, right. So let me consider two grids here. Why I am considering, I will explain during this stop. So this is two grids I have considered, and I am assuming the breaker is open here. Okay, and here I am assuming the grid as one is of grid maximum short circuit current, and the short circuit current after this is assuming it as a 40 kiloamperes, and the X by R ratio is of 40. Okay, right. And similarly for this, I am assuming the short circuit, minimum short circuit. This is I am assuming it as a minimum short circuit grid, minimum short circuit, and the short circuit current I am assuming it as, let's suppose, 25 kiloampere with the X by R ratio of the 40. Okay, so right, fine. So if we see the example here, so in this example, we have considered a simple network where the power grid or the utility is connected at the 33 kV, which is supplying the power to various loads connected at 6.6 kV voltage level as well as 0.415 kV voltage level. Okay, where the voltage is being stepped down from 33 to 6.6 and again from 6.6 to 0.415 kV through these transformers. Okay, here we here we have considered the bus couplers also, and the bus couplers are open in the normal condition. Okay, now in this case we have connected two different grids. Okay, in order to calculate the maximum fault current and the minimum fault current. Okay, so here we have connected two grids. One is to calculate the maximum fault current and second is to find out the minimum fault current. So as and when required, we will be switching between these two power grids. So first, let's understand the input data required for the short circuit analysis. So from the power grid point of view, this we have discussed in the space, just I am repeating it. This is very important. So in the power grid editor, go to the short circuit page. So here we entered three-phase short circuit current and single-phase short circuit current. Because without entering these values, your short circuit analysis will not be conducted. Okay, it will give an error. ETA will give an error. So these things are mandatorily you have to give it. You have to give three-phase short circuit kiloampere and single-phase short circuit kiloampere. So three-phase short circuit kiloampere I have given as 40 kiloampere and X bar as 14. Okay. Whereas for the minimum short circuit grid, the three-phase fault current and or the line to ground fault current values are I have assumed it as a 25 kiloampere again with the same X bar ratio of 14. Okay. So this is the with the ETAP we are entering these values. Whereas if you go with the EMT tools, so there you should not enter the values like this, like with the kiloampere and expire ratio. You should not means you do not have the provision to enter the values like this. So there you have to enter the values. That means whatever the short circuit means ratio of the grid, short circuit rating of the grid, that should be entered in terms of the positive means percentage R and percentage X. Okay, so you have to enter all the values in terms of the percentage R or percentage X. So we can calculate this also. There is a method to calculate this. So if we know the short circuit kiloampere of the grid and if we know the X by R ratio of the grid, so with that we can calculate what is the positive sequence percentage impedance, and that means a positive percentage R and positive percentage X. So just give me 1 second. Let me share one small calculation. Yes. Okay, fine. So here, so this is the short circuit source modeling calculation sheet. So in this, the voltage at the value means the voltage of the source or the grid, that is 33 kV. So that is what we have entered here. And the voltage automatically line to phase voltage or line to neutral voltage will be calculated. It's simple, 33 by root 3. And three phase maximum short circuit kiloampere is 50 kiloampere. That is what we have assumed. And the minimum fault current that we have assumed as 25. And for the single phase also we assumed it as a maximum is 50 and the minimum is 25 kiloamperes. Okay. And X by R ratio we have assumed it as a 14 for both the cases. Now if you see here, so this calculation is very simple. If you see on the right hand side, so what we are doing is similarly Z is equal to simple R plus X. You know the X value. So what you are doing is you are replacing that R value, means so your Z by R square equal to 1 plus X by R square. So you are calculating R value and accordingly you know the X by R, so you are calculating the X value. So with that you are going to find out the Z value. So the calculation is very simple here. But for the tools like PSCAD and all, so there you have to enter the values like this. 0.4986, 6.98404. So these are the values that you need to enter. Now, if I calculate, like if I see for this short circuit kiloampere of 50 kiloampere, which is the maximum short circuit, so it is 0.31162. I think there is some base so far. So, okay. So if you see the R and X values here, so this is per unit 0.31162 and 4.36275. These are the values in per unit. So here, these are the values. Okay. So these are the values. 3.499, 0.24, 3.4902. So with these calculations, we can verify that. Okay. So for the EMT tools, you need to give the values in this way. Whereas for the ETAP, it will directly take the values by just entering the values of kiloampere and the X by R ratio. Right, fine. Now the next point is in the power grid editor, we have to enter the values of short circuit kiloampere and the X by R ratio. Okay, that's it. That's fine. Next, coming to the transformer here. For the power transformer, we can use the same, we can use the data like the rating of the transformer, impedance of the transformer, these are same. But here in the short circuit, grounding is also important. Whereas in the load flow, grounding doesn't have any significant impact. Whereas in the short circuit analysis, grounding is very important. That means the transformer winding connection is very, very important. So you have to select the proper winding configuration of the transformer so that the fault currents, because ultimately the requirement, the main purpose of conducting the short circuit analysis is to find out the fault currents. So to get the correct fault current, so you have to give the proper winding configuration of the transformer. Okay, so in this, I have just assumed the transformer secondary winding as a solid grounding. Okay, right. Next, coming to the induction motor here, I just added just to show what are the details that are required. So that's why I just added here. So coming to the induction motor here. So in addition to the nameplate information, so this is the nameplate information which consists of the kilowatt rating, what is the voltage rating of this nominal rate, nominal current or the rated current of the motor with the efficiency and the power factors. Other than this, there is one more important point, one more important parameter that is required. That is called the lock rotor ratio, or you can call it as a percentage of lock rotor current. Okay. And the sequence impedance values. So these sequence impedance values are used for calculating the short circuit analysis or for doing the short circuit analysis, and same sequence impedance values will be used for conducting the unbalanced load flow studies, as well as these will be used in the harmonic analysis also. Next, let me add a generator also, so that yes. Let me add a generator also and assume it as a, suppose some 5 megawatt or 10 megawatt generators we can consider. So let us consider some 5 megawatt generator and the capability, okay, and the typical data I'm considering here. Okay, so for the synchronous generator, in addition to again the same, the nameplate rating of the generator, which is the megawatt, what is the kilovolt rating, the rated voltage of the generator, what is the rated power factor of the generator. In addition to these values, here the sequence parameters, the positive, negative, and zero sequence impedance values to perform the short circuit analysis. Okay. So these impedance are also value required, and especially we will go with the subtransient model because this will give you the worst case scenario, which will give the highest fault current, right? Because the impedance is very, very less during the subtransient condition. And here you have the option to apply the tolerance to the subtransient direct axis. XD double dash is the direct axis subtransient reactance. So here we have the option to apply the tolerance to the direct axis subtransient reactance. So once you enter the value here in the short circuit analysis, the software automatically considers the negative tolerance because the purpose is to find out the maximum fault current, right? So that's why tolerance will be taken on the negative side. Whereas for the load flow case, the tolerance will be taken on the positive side because that will give you the worst case of the voltage drop. So that's why for the short circuit analysis, XD tolerance or XD double dash tolerance will be taken as negative, whereas for the load flow, the same tolerance has been considered on the positive side, right? Now, so I hope this is clear up to this. Yeah, any doubts? If it is clear, then I will move further.
Okay, no problem. I can go.
Yeah, right. So now coming to this, the main purpose of conducting the short circuit. What is the main purpose of, let me note down some key points also here. So the main purpose of short circuit analysis is basically the short circuit study can be performed to determine the first one is to evaluate the electrical equipment, to evaluate the electrical equipment short circuit withstand. Okay. So the first one is the first purpose of conducting the short circuit is to evaluate the electrical equipment short circuit withstand current, which will verify the basically what it will verify. It will verify the protective device or the circuit breaker or the fuse, whatever it may be, device making capacity. Next is the breaking capacity and thermal withstand capacity. Withstand capacity of various protection devices. Okay. So the first objective of conducting the short circuit analysis is to determine the or to evaluate the electrical equipment short circuit withstand current, which will verify the making capacity, breaking capacity, and thermal withstand capacity of various protection devices connected in the network. This is the first purpose. And the second purpose of conducting the short circuit study is to calculate the fault currents, to calculate the fault current, which will be used for selecting the which will be used for selecting the settings of various protection devices. Selecting the settings. Selecting the various settings of the various protection devices. So, can you wait 1 second? Okay, fine. Right. So the purpose of conducting the short circuit study is clear. One is to evaluate the electrical equipment short circuit withstanding capacity, and second is to calculate the or to find out the fault currents, and that can be used as an input for selecting the settings for the various protection devices. Okay. Now coming back to this example, first what we will do is we will first go through how the switchgear or the circuit breaker vendors select the ratings of these equipments. Okay. First we will try to understand that. So in order to select the circuit breaker or the switchgear rating, it should satisfy 3 conditions which I have explained here. That is, close this. Yeah, one is the making capacity, breaking capacity, and thermal short circuit duty. So peak making duty occurs. So the making capacity, if you see here, it will be considered as a peak making capacity. Okay, so the making capacity is the peak making capacity. So the peak making capacity, if you draw any waveform here, oh wait a second, let me prepare an MS Paint. Right. Suppose if you see, if you take the case of any case, so normally the maximum peak current or the peak making capacity occurs at half cycle. This occurs at half cycle, which is the maximum instantaneous fault current magnitude seen by the protective equipment during the fault. Okay. Is it clear? So the making capacity, which is, we will call it as a peak making duty, or we will call it as a peak making capacity. This happens at the half cycle of the waveform, which is the maximum instantaneous fault current magnitude seen by the protective device or the protective equipment during the fault. Okay. Next, coming to the breaking capacity or the breaking current. So this is nothing but the asymmetrical current. This is the asymmetrical current at the instant of break of the circuit. Good. Break of the circuit breaker, which consists of opening time of the circuit breaker and the relay opening time. Okay. Next is the thermal withstand capacity. This will be generally defined for the 1 second. That means the withstand capacity of the circuit breaker, 1 second or 3 seconds short circuit duty. So in order to select the protective equipment, it should satisfy all these 3 conditions. Okay. Now, we will try to validate these 3 in the ETAP. So for that, let me enter some data inside the circuit breakers. So what I am doing is I am going to select the random data from the vendor provided information. Let's say, for example, for this circuit breaker. Okay. So go to the rating page here, and here go to the library. Here you have the list of circuit breakers that are available in the ETAP default library. So what I am doing is, instead of selecting here, we can directly enter the values also. So, okay, the rated current of the circuit breaker, we don't know. So for that, what we have to do is, you just go to the load flow, run the load flow here, and check the currents. So here, if you see here, that current is of 13,000, no, this one, 1371 amperes. So what I am doing is I am just selecting the rating of the circuit breaker as, let's suppose I am using some 2000 ampere circuit breaker, and the breaking current I don't know. So what I am doing is I am just selecting it as a 20 kiloampere, for example. Okay. So this is the high voltage circuit breaker, which I have given the rated ampere of the circuit breaker as 2000, and the rated voltage is of 6.6 kV is not available. So we will consider the 7.2 kV circuit breaker. Okay, right. Or okay, This is one method, and you have to enter the making peaks values and all from the circuit breaker datasheet, or you select any breaker with the rated voltage of 7.2 kV. Rated kV is 24, 24, 24. Okay, 12 kV also you can select, and 12 kV, yes, 12 kV, 1600 ampere, 12 kV, 2000 ampere breaker. Click OK here. Now, if you see this, the short circuit withstand capability of the breaker is, we have selected as 20 kiloampere. Okay, 20 kiloampere. Breaking current is 20 kiloampere, but the making peak is 50. If you notice here, the making peak is 2.5 times of the breaking capacity. So you can observe the same in the circuit breaker data sheets also. So the making peak is approximately 2.5 times of the breaking capacity. So as a thumb rule, generally the manufacturer selects the making peak value, which will be 2.5 times of the breaking capacity. Okay. And we will try to derive the making peak factor also, like how this 2.5 will come. And here, this is the time delay, or you can call it as a time constant. Okay. So generally the time constant will be selected as 0.045, 45 milliseconds. Is the typical value as per IEC 60909, IEC 62271 standard. For the circuit breakers, it is 62271, medium voltage circuit breakers. Okay. So the medium voltage circuit breaker, we have considered the minimum time delay, or we will call it as a time constant as per IEC 62271. Okay. And this gives the percentage DC of 36.79. Okay. So this gives the percentage DC of 36.79. Fine. So this is about the medium voltage circuit breaker. Then if you go to the low voltage circuit breaker here, go to the low voltage circuit breaker here. Yes. Now here for the low voltage circuit breaker, here you have different values. One is, let me select some more breaker of some 60 kiloampere or something. 60 kiloampere is too high. You have to select the power circuit breaker here. And let me select some 42, especially 63H or 2000, just some random breaker. I am selecting it. Okay. So here you have the different values. One is the service breaking, ultimate breaking, and making peak. Here it will be generally the making peak of this LV circuit breaker will be approximately 2.1 to 2.2 times of the circuit ultimate breaking capacity. Okay. Right. Now let's try to find out the values here. Let's try to find out the values of breaking capacity and the making peak, and try to find out what is the percentage DC component at this minimum time delay of 0.45 seconds. And we will try to calculate it for 0.035 seconds also. Okay. Right. Fine. We know there is a procedure mentioned in this IEC 62271. This is the standard applicable for MV circuit breakers. Okay. So as per the circuit breaker, as per this IEC 62271, the MVCB shall be type tested with a tau, or the time constant, of 45 milliseconds. 45 milliseconds. Okay. So how can we calculate it? I will just explain a simple procedure for this. First, the time constant tau is nothing but your L by R. Correct? So this L by R is around 0.045 seconds, or it is a 45 milliseconds. Now, if you, 0.045 seconds, right? Now, if you multiply this tau by omega, so the omega tau, so this is equal to omega into L by R, correct? No? So this is nothing but your X by R. So this is your X by R. So how can we, what will be the X by R value? What will be the X by R value? So this will come if you multiply this with omega, which is equal to 2 pi f, equal to 2 into 3.1415 into 50 into L by R, correct? It is equal to 0.045. So it will be 14.13. So your X by R value is 14.13. This tau we have assumed as per the 62271 standard. Tau we are assuming it as a 45 millisecond, and omega tau, which is the nothing but your X by R. So that X by R is coming as 14.13. Right. Now let's try to calculate what will be the peak capacity. How to calculate that? That we will try to find it out now. So as I told you, as a standard time constant, we are considering 45 millisecond for the medium voltage circuit breaker. But yeah, for some special applications and depending upon the voltage level, you can consider the various time constants provided as per the IEC standard. So, but tau value is 45 millisecond we are considered, which is also equal to L by R. If you multiply that with the omega and tau, it will give you the value of X by R. Okay. So X by R is derived as 14.13, which is nothing but the multiplication of omega and the tau. Now, as we have seen in the circuit breaker editor, here we have provided the value, breaking current value as 20 kiloamperes, right? So I can assume it as a IAC symmetrical RMS. IAC symmetrical RMS equal to 20 kiloampere. Okay. And I told you this is the making peak, right? So this is the making peak. So the making peak happens at the half cycle, correct? So let it note down also. Making peak happens at half cycle. Here also I have mentioned here. So making peak happens at the half cycle. Right. So now what is your IAC peak? IAC peak, calculate with this IAC symmetrical RMS, that is equal to square root of this IAC symmetrical RMS. So that is equal to square root of 2 into 20 kiloamperes. So this is your IAC peak. And coming to the IDC peak, now to calculate the IDC peak, we have to understand one small concept. I think I have in the last class I have touched upon. So just me explain it once again. Let me draw this. Let's suppose this is your voltage waveform. Okay, this is the time axis, and this is your voltage axis. And here, let this is the current axis. Okay. So, no, just one second. Just 1 second. Okay, fine. So we know, and this is the voltage axis, this is the voltage waveform, and here we will try to plot the current waveform. Okay. We know that the total fault current consists of both AC component and DC component of the short circuit current. Correct? The total fault current consists of both the AC component and the DC component of the short circuit current. So the DC component will be present in the system if it satisfies two conditions. First one is the electrical system, because mostly our electrical system is inductive. So the current will lag the voltage by approximately 90 degrees. So the first condition is, let me write it down here. The current should lag the voltage by 90 degree approximately. And that means if I draw the waveform here, it will be, let me create an arbitrary axis also. Right. So it will be something like this. I think I'm very bad in drawing. So at this point, it should be maximum. So this is your maximum point here. It should be the maximum. Okay. So we can draw like this. Simple something like this. Okay. Okay, fine. So here, as I told you, if the fault occurs, that means the DC component will be present in the system if it satisfies the two conditions. The first condition is the current lags the voltage by 90 degree because most of our electrical system is inductive, right? So if a fault occurs at the 0 point on the voltage wave, the current should be maximum. So this is your 0 axis and this is your shifted 0 axis. Why it is shifted, I will explain. So when the if the fault happens at the 0 point on the voltage wave, the current should be maximum. Okay. So here you can observe that at the 0 point. So this is your 0 point and this is your 0 point. So here the current is on the negative maximum, whereas here the current is on the positive side maximum. Okay. And the second condition that needs to satisfy is at time t equal to 0, the fault current should be 0. The fault current should be 0. Okay. So in order to satisfy these two conditions, there will be a shift in the 0 axis. So this 0 reference axis will be shifted to this point, which is the DC component of the fault current. So this is the DC component of the fault current. And here this is also the DC component of the fault current. Okay. So this part is the DC component of the fault current. And again, same, this portion is also the DC fault current, the DC component of the fault current. Okay. So as you can observe from this curve, the peak value of the fault current, again, this is same √2 of IAC symmetrical RMS. And similarly, which occurs at the half cycle. And again, here, this is also the √2 of IAC symmetrical RMS. Okay. Here, this is √2 of IAC symmetrical RMS. So what you have to do, you have to calculate that value. So IDC peak is equal to √2 times of square √2 of IAC symmetrical RMS, which is of 20 kiloamperes. Okay. So IDC peak is also 28 point. Sorry. This IDC peak we have to calculate at time constant tau. So here this will not come. So this will be square root of, the formula will be something like this, √2 of IAC symmetrical RMS into e power minus t by tau. So this is the DC component of the fault current. So if we apply the same formula here, this is equal to, what is the √2 of IAC RMS, which is equal to your IAC peak. This is equal to 28.28 into e exponential of minus t. T is what? 0.01, 10 milliseconds, right? Divided by 0.045. So this is coming as 22.648 kiloamperes again. So the making peak is nothing but the summation of both IAC plus IDC. So this is the vector sum, so we cannot add it arithmetically. So what you have to do is you have to square root of this current into this current plus this into this. So this is coming about, this is coming of 1 second. So this is the making peak, this is the making peak, right? So this making peak is nothing but the summation of the AC current plus the DC current. So this is simple 28 plus 22 kiloamperes. So which is of 50.93 kiloamperes. Now the making peak factor, is nothing but your 50.93, which is your making peak current divided by what is the breaking current or the symmetrical RMS current, that is 20 kiloamperes. So this is the factor which is coming as 2.5. So that is the reason why the making peak, if you see here, the making peak of the circuit breaker is approximately 2.5 times of the breaking current of the circuit breaker. Okay, fine. Just 1 second. Yes. So the making peak will be always for the medium voltage circuit breaker. It will be approximately 2.1 times of the breaking capacity of the circuit breaker. You can verify any circuit breaker data sheet. So it will follow that IEC 62271 standard. So that factor will match. Okay, right. Now, now same coming to this also here for the LV breaker also is the same. Now next coming to performing the short circuit analysis. So to perform the short circuit analysis, what we have to do, you have to go to the short circuit analysis tab and go to the study case here. So here, one question. Okay, I will answer this question after this. Okay, now if you enter into this study case, so here you have the option to create the fault of all the buses, and you have the option to select that. Okay, so for that, what we have to do, I'm just selecting all buses. That means the fault will be created on all the buses of this network. Okay, if you just select this all buses and connect it here, so it will come. Next, coming to this here, you have the different options, whether you have to include the impedance for the MV motors or LV motors, and motor contribution, how it will be. So all those things can be selected here. Yes, here this is important. The standard which we have to see, that is of IEC 60909 we are following. So here the standard is the IEC, and this is important. Short circuit current, which is the, suppose this is called the C factor basically. So if it is for the maximum short circuit current, the C factor will be considered as 1.1, means up to 1 kV, the C factor is 1.045, 1.05, and 1 kV to 230 kV it is 1.1. So as this is the medium voltage system, so the C factor will be considered as 1.1. Okay. And this C factor 1.1 should be means okay, that I will explain. Right. Next, coming to the device duty. Device duty is based on the total bus fault current or the maximum through fault current of the circuit breaker. So that can be selected here, because it should be carefully selected. Why? Because suppose if I want to evaluate the device duty of the circuit breaker. Okay. So when a fault happens on this bus 2, your motors will also contribute, your lump loads will also contribute. But the fault current flowing through the breaker will be different than the bus fault current, right? That I will explain while we are doing the simulation, so that we will see that. So here what you have to do, you have to select the device duty based on the maximum through fault current flowing through that circuit breaker. Okay. And here the calculation method X by R, this is the that I have explained in the last class. And adjustments, so about the impedance tolerances, so all those things can be selected in the adjustments tab. So just click OK. And here you have the option to run the 3-phase device duty calculation. Yes. So now if you see here, the fault current of this bus is 29.45. But whereas the fault current flowing through the circuit breaker, that is 21 kiloamperes. So why the difference is there? Because the loads are contributing to the bus fault. So that's why your bus fault current will be differ from the actual fault current flowing through the circuit breaker. So that's why you should be cautious when you are choosing this option. So when you are evaluating the device duty, so that time it should be selected based on the maximum fault current flows through the circuit breaker or the protected device, but not the bus fault current. Okay, because if you select this one, so probably you may end up with the wrong results. Right. Now, once you have done the duty here, so what it will give? It will give the three-phase short circuit value of all the buses. Three-phase short circuit value of all the buses, and it will evaluate whether the circuit breaker ratings are sufficient or not. Because till now we have given the circuit breaker rating only for this. So for just check, go to the alert view here. Yes. If you see here, this is the circuit breaker 2. The making peak is rated is 50 kiloamperes, but the operating value is 56.271. 50 kiloampere is the breaker making capacity that we have selected, but the actual operating value it is 56.271. Similarly, the braking capacity is 22.545, whereas the operating it is 25 point. So what we have to do, we have to select the next higher rating of the circuit breaker. So let's suppose the braking capacity I am increasing to 25 and making current will be 25 into 2.5, it will be 62.5, and here the circuit breaker thermal capacity is also increased to 25. And let's run the device duty again and check for the alerts here. So now your thermal energy is not sufficient. That means your thermal withstand capacity, again for the 25 kiloampere also, your thermal withstand capacity will not be sufficient because we have selected it for 3 seconds. So if you select it 1 second, probably that may match. Let's just try that also. Yes, no, still it's not matching. So what we have to do, we have to select the next higher rating breaker. So that is of 31.5 kiloamperes. So 31.5, and if you calculate this, 31.5 into 2.5 is the making peak, which is of 78.75 kiloamperes. 75 kiloamperes. And now run the device duty here. So now see, there are no alarms. That means the circuit breaker should be, even though the rating and the fault current of the circuit breakers are well within the limits, but to meet the thermal withstand capacity requirement, so you have to select the circuit breaker of 31.5 kiloampere, but not the 20 kiloampere or the 25 kiloampere circuit breaker.
So what if time is a 3 second then? Can you run for that?
No, see, that is the withstand time. Yeah, okay, we can run that 3 seconds. So let's user defined is also 3 seconds. So let's run the device duty here. So here the 3 seconds also it will be okay, right? So that's why in this way you have to select the circuit breaker rating. Just not by checking the fault current and the rated current, you have to perform the device duty calculations, and you have to check whether your making peak, braking current, and the thermal withstand capacity of the breakers are well within the limits or not. Okay, right. Hope this is clear up to this. Yeah.
Sir, this
Next.
arrow indicating, can you explain this arrow indicating the contribution of fault?
Sorry.
This arrow indicating the fault current, can you explain?
Which one?
This
This
arrow,
one?
yeah.
Yeah,
to the
this
bus.
is nothing. Yeah, the arrow is nothing but the fault current means if a bus fault happens on the bus 2, the contribution from the 33 kV side is 21.847, whereas from the lump load it is contributing 7 kiloamperes and the motor is contributing 0.183 amperes. And here this is showing it as 0.448 because some lump load has been connected here. So if you add all the currents, it will be 29.454. Okay.
Yeah.
But the major contribution is from the motor loads only, constant power loads. Okay, right. Fine. So this is how we can validate the 3-phase device duty calculations, and this is for the single-phase device duty. This is generally, as you can see, that is applicable for single-phase UPS and single-phase device duties. But here this is the 3-phase. So this is the 3-phase device duty calculations. And here one point which I want to highlight here is this device duty calculations will be verified for the maximum fault current. That means when you select the C factor maximum, then only you can able to perform the device duty calculation. Suppose if I select the minimum value here, if you see the device duty is getting grayed out or it is getting disabled. So that's the reason you should be cautious that because you are verifying the circuit breaker duty for the worst case scenario. So that's why you have to always select the C factor as maximum. Okay, fine. Next, so this is about the device duty here. And coming to the 60909 here, so if you run this 60909, what happened? You will get all the fault currents. Device duty, in the three-phase device duty, we are getting only three-phase fault currents, right? Whereas if you perform the simulation with 60909, here you have the option to get the positive sequence, means phase to ground fault current, ground means double phase to ground, three-phase fault currents, everything we can get. So that can be selected from here. So depending upon the fault type, here the fault type is selected as three-phase. So that's why we are getting three-phase fault currents. If it is single phase, so if you want to display both the values, and here you can see this is the fault current values R by B, individual for the single phase to ground fault. So here you have the option for LLG faults. So you can see here, these are the LLG faults. And 25.495, 180 degrees exactly opposite. And here you have the option to select that. Option can be disabled here. Okay, right. Next. So this is about the running the fault current faults, means to find out the fault currents for different faults like phase to ground, phase to phase, double phase to ground. So that can be selected from here. And here another option, that is transient short circuit. So this will follow all these three, means the device duty and the 60909 follows the 60909 standard. Whereas if you want the time variant fault current, so that can be selected using this 61363. Now, if you perform the 61363 and if you go to the short circuit reports, and let's suppose if I want to verify the bus fault current of this bus 1, for example, or you can select the bus 2, that will be better. Okay, so here you can able to find out what is the total current, AC symmetrical RMS, IDC component and the envelope. So click here. So here, see, this is the time varying fault current. Why it is time varying fault current? Because here we have connected a generator. Okay, so if you see here, the fault current at this point is near about 75.1 kiloampere, whereas here it is 63.5, 55.5, 47.8, 45. So it is gradually reducing, right? And this is the DC component. So the DC component initially it is 41.5, it is keep on reducing. Similarly, initially it is 100%, and after 100 milliseconds, it is coming to near about 18.2%. This AC component, this is the AC symmetrical RMS, and this is your IAC envelope, I envelope current, total AC plus DC current. Now let's suppose if I switch off the generator here and again run the 61363 and try to go to the plots here again. So here the fault current is almost the same. Okay, so that means it is considering it as a fault nearer to the generator. So if a fault is away from the generator, if the fault is very near to the generator, so then these components will be too high. Okay, so this will be, if the fault is far away from the generator, the first cycle symmetrical RMS is almost matches with the remaining cycles also. But here, by default, IAC 61363 considers it as a fault near to the generator. So that's why your AC waveform or the AC current is gradually reducing because of the DC component of the fault current. So this is your total current, IAC plus IDC. Okay. So with this, you can get the report also. Just to check this, go to the viewer. Yes. So next page, if you go to this. Yes. So if you see here, this is your time and this is your cycle. And what is the maximum fault current? What is the fault current? And in that, how much will be the DC? What will be the total AC symmetrical RMS? What is the component of the DC? So like this, you will get the time varying fault current with IEC 61363 standard. Whereas if you go with the 60909 standard and check the report, here. So complete report. Yeah. So if you go through this, so you will get only fault currents, nothing else. Here, if you see here, this is the maximum symmetrical three-phase fault current and what is the single phase to ground fault current. That's it. But this will not give you the time varying current, time varying fault current. This will give you the maximum fault current flowing through that bus. Okay. So those values that we can get it here. One is you are getting the initial symmetrical current. Second is you are getting the peak current, breaking current, and the steady state currents. Okay. Fine. So this is about the short circuit analysis. So short circuit analysis module is very simple. So one thing is you have to, with the short circuit analysis, you can validate the device duty. And second is you can find out the fault currents, and these fault currents will be helpful to find out the settings of the circuit breaker. Okay. To find out the settings of the circuit breaker of the relays, basically to do the protection coordination. So we need the fault currents, right? So to find out the fault currents, again, that will come from the short circuit study only. Even in the relay coordination also, we will perform the short circuit analysis because we need to find out what is the maximum fault current flowing through the circuit breaker or the relay connected.
Sir, we lost your voice. Sir, we lost your voice.
And you have the option of the short circuit analyzer just as the load flow analyzer here. So here you can compare the results also. But here, as we have only one configuration, so here we are not getting it. But yes, if we want to create another configuration, normal one, and what is the circuit breaker? Okay, apply.
Hello, can you please
Yes.
repeat the last 3 minutes of what you said because your audio went off.
Sorry.
Your audio went off for a few minutes. The last 3 minutes of what you said, the audio went off, so we didn't hear you.
No, yeah. See, what I am telling is this is the way how to perform the device duty calculation 60909 and 61363 calculations, because this 61363 will give you the transient short circuit, that means which will give you the time varying fault currents. Okay. So that is what I am explaining. And here as a load flow analyzer, here we have the option to analyze the short circuit analyzer also. So for that, what we have to do, we have to create different configurations. So two configurations are created. One is the normal configuration. That means these two circuit breakers are open. The tie breakers or the bus coupler breakers are open. So now what I'm doing is I'm creating another configuration, normal one. In this CB12 and CB13 will be open. Go to the normal configuration here, and these two breakers will be closed. So CB12 and CB13 will be closed, whereas CB11 and CB9 will be open. So CB9 and CB11 will be open. Just click apply here. Now in the normal configuration, if you run the short circuit, find out the short circuit fault currents. So here by default configuration, I've shown it as a status close. So this is also close. Okay. Now, if you run the device duty calculations and go to the short circuit analyzer, so here you can have the option to select. So in the nominal kV bus 1, what is the nominal kV of the bus? What is the IK double dash IP? That means this is the subtransient fault current, AC fault current, IP, maximum peak, IK, and standard. Okay. So this is how you can check, and you can update these values in the data block also. What is the type of this? What is the C factor that you are considering for this? And what is the rated peak current of this circuit breaker? So everything you can select it from here. Okay. So here you have the option whether you have to check the study type, 3-phase duty type, because here we are considering 3-phase network type. So here the study type should be the 3-phase duty only. Okay. So these are the general selections, what we have selected in the protected devices. Okay, fine. Yeah, so this is about the short circuit analysis. So short circuit analysis is simple, so nothing much in that. But yes, if you want to learn, you have to refer some standards. As I mentioned, IEC 62271 standard, which is for the medium voltage circuit breaker, and 60909 will give you the how the fault currents will be calculated and all. That is completely depending upon the per unit systems, how the contributions will be. So everything has been clearly mentioned in 60909 standard. So this is about the short circuit analysis, how to perform it. Yes. Yeah. Any doubts in this? I will take up the questions now. Let me
Hi,
share.
Venkatesh.
Yeah.
Yeah, my question is that I have a existing distribution system which is fed through around 6 gas generators,
Okay.
around 19 megawatt each, right?
Mhm.
Now I'm doing extension of some of the extension of the network. So
Yes.
I'm adding one 6.6 kV bus plus one 400 volt bus with the help of some transformers, right?
Okay.
Now I don't have the ETAP model of the existing network, but
Mhm.
I have the report of the existing network. So
Okay.
with this report, I mean, only the input models are mentioned, normal stuff that is mentioned on the report, right?
Yes. Yes.
So with this report, can I do the impact of the new extension?
Yes. Yes. That can be done. Let me share my screen here. Yes. So here, if I go through the report here, complete report, viewer. This is the report here. Yeah. Here, this is the max short circuit report, right? So this is
Yes.
the short circuit report of this. So what is the maximum lump load? Yeah. Here the total contribution of the bus. What is the maximum fault current that has been flowing through the bus? So that is 63.955 kiloamperes. Similarly, for the bus one, it is 41.87. This is the total fault current, right? Contribution from the transformer, contribution from the loads, lump loads, motors, everything and all. So this is 41.871. So you have to at least model the network such that the 41.871 kiloamperes will be flowed. Then you start adding the network and you can do the ETAP analysis. That can be
So
done.
I have to draw the existing model again based on these
Not to
parameters.
complete detail, yes. Based on this parameter, at least you have to ensure that this much fault current will flow. Then you can
Okay.
add on the network.
From the bus where I am taking the tap
Yes,
for,
yes,
right?
yes, yes, yes.
Okay. Okay. And then all the input parameters should be as per this report, right?
Yes, 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 yes.
Okay. Okay. And I need to match
Okay. So this is
41.87 of
yeah.
that bus
This
where
is
I'm
one
taking the
method,
tap.
and you can if you have for example, your 6.6 kV network as you are telling that. So this is
Yeah.
your existing bus, and here if you are connecting 6.6 kV network,
Yeah.
one more thing you can do is you can do the analysis for that complete 6.6 kV network, and what is the fault current flow from the 6.6 network to this bus to that can be calculated, and you can sum both. So that will also valid.
Yeah, but in both the cases, I have to draw the whole network, existing network,
Not
right?
required, not required, not required.
So how do I represent the existing network through some and only one bus I will draw?
Yes, only one bus, and here you can add some lump load such that it will contribute this much of current. You can do like that.
Okay. Okay, but what about the source of that bus?
Source should be the grid. It should be
So-
it should be like, because you don't have do means model to the generators and all, it is not required. You just model it as a grid and ensure that the lump load, with the help of the lump load, you will get the fault current of that much of milliamperes.
In that bus.
Yes.
And what parameter should I use in the grid to represent the whole existing network?
So this is the maximum fault current, as I told you, maximum fault current is the expense.
Okay.
Okay. Right.
All right.
Yeah.
Understood.
Yes.
Thanks.
Next question. If our network, if for our test network, a customer wants to connect our LB, how can we calculate the short circuit and X by R ratio of that bus? And that how can we get actually from the ETAP? So see, this X by R ratio from the ETAP is very simple, because we know what is the percentage R and percentage X up to this. And with that, you can find out the X by R. But generally, we will not bother about the X by R for the slow upstream or downstream network. But yes, from the grid, whatever the X by R, that you will get it from the utility or from the grid operator. Next question. Why sometimes SLG fault? Yes, this is SLG fault. MVA is higher than the 3LG fault. This is because of the zero sequence X0 by X1. If X0 by X1 is less, so then your X1 value will be more than your X0, right? So in that cases, your SLG fault will be more than your three-phase fault, which will generally happens in case of the transmission lines. And what are the usage time of varying the ISC? Sumedha, I didn't get your question clearly. What are the uses of time varying ISC? Okay, where you are using this ISC? Okay.
Yeah,
So the time varying ISC basically we will use to find out, like, see, let me explain me in this way. If you see the network here, this is the circuit breaker 2, and the circuit breaker 2.
The screen is not.
Okay. Sorry.
Not sure.
Yeah. Here, if you see the circuit breaker 2, the same circuit breaker, here the percentage of the DC, that is 36.79%, right? At the contact parting time. So this is the percentage of the DC contact at 45 milliseconds. So when you run the time varying this one, like if I run the 61363 and if I go through this and select the bus 2, click on OK here. So here you have the option at the 45 milliseconds, or you can check in the report also. At 45 millisecond, whether the percentage DC is within the limit or not, that you can check. Yes. So here this is 4 milliseconds. Here this is, I think this has been run up to 35 milliseconds. So generally this will be evaluated to find out what is the means at 45 millisecond, what will be the DC component of the fault current. So if you see here, the DC fault current is coming down to 45.79. So it will keep on reducing this. Okay. So it will keep on reducing. So that means your DC fault current, your DC component of the breaker, what you have selected is less than this only. Okay. Suppose if it is something like 80 or 85 at the, even after 35 millisecond, if it is 85% and at 45 milliseconds, suppose if you are considering it as a 30% of the breaker capacity, so then that is not correct, right? But this is almost nearer to this. 35 millisecond, it is 45.79. But what the thing we have selected, the breaker, it is of DC component can handle it as of 36.7. So this is almost equal. Whereas suppose at 35 millisecond, if the percentage DC component as per this one is, let's suppose 80%, and you are selecting 36.79. So probably the breaker may fail during the breaking time. Okay, just to validate that only we are using this IEC 61363, and to find out how the fault current is varying with respect to time, to find out that this 61363 will be used. Right. Next, ISC peak formula, IDC peak formula. So that I have already shared. I will share the Excel. Next, how to check the cable short circuit withstand capability. So this is simple. because for the cable also there is a short circuit rating of the cable, the maximum fault current that the cable can carry depending upon the size of the conductor, right? Because the size of the conductor will also be selected depending upon the fault current that it can handle. So, and with respect to the whether the cable has been designed for fuse operating time or the circuit breaker operating time, if it is for fuse operating time, you are sizing the cable for the let through current of the fuse. If it is for the circuit breaker, so the fault clearing time you are considering as a 0.120 seconds or 120 milliseconds. So I square R, it's nothing but simple. I square R, so maximum fault current flowing through the cable square into the maximum time that it can withstand for that current. So with that, we can check the cable short circuit withstand capability. Right. Yeah, any further questions? Right. Yeah, if it is clear, then next week onwards we will start this continuation of this, that is the relay coordination will start, and we will try to do the relay coordination for the LV circuit and the medium voltage circuit, and we'll go to the one sort of settings in the high voltage circuit also. Okay. So probably that will take another three classes maybe for the relay coordination. So that we will try to understand the relay coordination, because that is the continuation of the short circuit. Okay. Fine. Okay. So yes.
Minimum short circuit, you are modeling the minimum grid.
Yes.
Short.
Yes.
So where it is used, sir?
So see, this is minimum fault current. Generally for the device duty calculations, that minimum short circuit is not required. But yes, for the relay coordination, you have to check the coordination from the minimum short circuit current to the maximum short circuit current. Okay. Suppose if you are maintaining 200 millisecond coordination time interval between the downstream device and the upstream device, that 200 milliseconds should be maintained from the minimum short circuit current to the maximum short circuit current. So in that case, we will use the grid minimum short circuit current. Okay. So during the relay coordination, we will use the grid minimum short circuit current. Okay. Because for the short circuit, as of now, what we have studied, that is for the maximum fault short circuit current requirements only. So that's why I've considered only the grid maximum short circuit current. This minimum short circuit current is required for the relay coordination time.
Okay, sir. Thank you, sir.
Yeah. Fine. So if it is clear, then we can wind up the class for today. And in the next week, we will continue with the relay coordination. Okay. Yeah. Yeah. Okay. Thank you. Thank you all.
Thank you.
Thank you.
Mm.